Bhaskar Vairamohan. I am with the Electric Power Research Institute and I currently manage industrial energy efficiency related projects. Today we are going to talk about some of the aspects of ladle preheating, where it is used, why it is significant, what is the current trends in the industry, what are some of the challenges faced by the industry, what are some work that EPRI is doing along with its members and industry, and some resources. And when I speak about ladle, sometimes first thing that comes to mind is the soup kitchen, the utensil to serve soup. That's a ladle too. But here we are talking about ladles used in foundries where they melt metals. So this is a big container that carries molten metal. Before going to the topic, I just wanted to give a brief introduction about who EPRI is. EPRI is an independent non-profit organization which brings together scientists, engineers, academic researchers, and industry experts together to solve a lot of complex problems and conduct tests and research and provide results that addresses reliability, efficiency, health, safety, and the environment. We are located in US, but we have members who are electric and electric utilities who are around the world. So with that brief introduction, let's go into the subject of the topic today. Why are we interested in ladle preheating? EPRI has a energy efficiency group, and within the energy efficiency group there is another center called Industrial Center of Excellence. And the purpose of the Industrial Center of Excellence is to go and conduct energy assessments at various industrial customer sites. On one such industrial assessment in 2013, we identified a customer who was a foundry, and this customer was trying to find a better way to heat their ladle. And we will see their uh, facility briefly during the slide presentation today. So we got back from the assessment and we were looking for other alternate technologies to preheat the ladles. And what we found was there were no major vendors who make a turnkey solution, a turnkey operation of providing a ladle to the foundry. So along with our member Alabama Power, who is based in Alabama, USA, they have a technology application center, and we started evaluating few designs in the laboratory. And this project is currently ongoing, funded by EPRI and Southern Company, who is the parent company of Alabama Power. And we also organized a workshop to bring utilities, vendors, and customers together to find some solution. So during this presentation, I will provide some of the test results and what we found is the state of the industry and what are some of the health and safety concerns that the workers face here in these foundry operations. As I mentioned earlier, ladles are used in foundries. These are refractory lined steel shell that transports molten metal from melting furnace to the pouring line. And there are several different kinds of ladles or ladles: transfer and casting, porous plug ladle, teapot spout ladle, bottom pouring ladle, lip access ladle, and so on. And on the right, you can see some of the images of different types or different kinds of ladles. So what are the size? Is it small or big? So small foundries carry a smaller version of the ladle, typically 50 to 500 pounds. But there are some smaller version too that are used by the pawn stores where they melt the golden rings and other ornaments to make into a ingot. But larger foundries like steel foundries have larger, like 3 tons to 350 ton, huge ladles that typically is transported using a rail cart or a crane to lift the ladle because of its size. So you could see below two examples of a small 300-pound ladle with a wheel that could be moved by the workers and a big 40-ton ladle used in a steel foundry that needs cranes to lift them up. So the typical process involved in melting to casting is there. The melt furnace is where any type of scrap or ore of metal, for example iron ore or anything similar to that, is melted, or even ingots, or they are melted to form a molten liquid. And this molten metal is then poured into a ladle, and with the help of a crane or other mechanism, it's taken to another side, another location, where it is called the pouring line, where the molten metal is poured into a into a cast to make parts, metallic parts. So in this process, one thing to note is that why do we need to preheat the ladle? Because the molten metal is of the order of thousands of degrees Fahrenheit, sometimes 3000, 2000, 3000 degrees Fahrenheit, depending on the metallic constituents. If the if the ladle is not preheated, what typically happens is it is treated as a cold body. So heat always moves from hot body to cold body, and a lot of the heat from the molten metal, is transferred to the ladle, and there are a lot of issues associated with it. First one is explosion. If the ladle is not preheated, it may contain moisture from the air or in the refractories, and this moisture could turn into a steam, and during this process causes a big explosion. And this is not a thing that you want to see in a foundry, an explosion where the molten metal is sprayed everywhere. So this is a big safety concern for the foundry. Second is skull formation. And when I talk about skull, it's not the human skull, but metal, when it solidifies, when the hot object comes to contact with a cold object, instantly it becomes a solid from the liquid form. When it happens, it needs more maintenance and more labor to scrap that solid metal. And in that process, it affects the metal quality and also affects the inner lining of the ladle. Thermal shock. Thermal shock is when a hot uh, molten liquid of the metal touches and gets in contact with a cold ladle surface. In that case, it experiences a thermal shock. This is not something new. If you take a glass pot and heat it in a microwave, and then instantly if you cool it with dry cold water, you can see that the glass breaks because it is a thermal shock that is experienced by the glass. So it's a similar concept. Some of the other reasons are the temperature loss reduction. What do I mean by that? When typically in a foundry, the melting furnace and the casting line are in two separate locations, it may take 2 to 5 minutes to go from one location to the other. And during the process, the liquid metal is going to be exposed to atmospheric temperature, which is probably around 70 to 100 degree Fahrenheit. So there may be a loss of temperature if the molten metal is not transferred using a ladle that was not preheated. So it helps in reducing the temperature loss. And finally, lining life. What do I mean by the lining life? On the right hand side picture, you are seeing a big ladle, and it's a steel ladle, but inside the steel ladle there is a refractory material, a kind of insulation material that is laid around it, and over a period of different pores of molten metal, the lining gets damaged. However, to improve the lining life, you preheat the ladle so as the refractory material is uniformly heated under controlled temperatures and not exposed to thermal shocks. So these are some of the reasons why heating the ladles is very important in a foundry operation. What are some of the fuels used for ladles currently in the industry? In many different parts around the world, natural gas is by far the most commonly used fuel. And on the picture on the left, natural gas, you can see the top of the lid is kept little bit open because the natural gas is the combustion happens, and the combustion gases are sent inside the ladle, and the gases go inside and come out and escape through that opening. And all the fuels other than electric are kept open, the lid is kept open to so as to allow the combustion gases to escape. And this is a big nuisance in the foundry, and I will tell you why in just a few minutes. Oxyacetylene fuel, oxy-fuel, is another fuel that is used. Liquefied petroleum gas or liquid petroleum gas, LPG, is another fuel. Distillate oil is another fuel. These are some of the major fuels. There could be other things such as coal and wood chips and things like that. That's not very common. But there are few percentage of foundries in the world still use electric, and it could be electric resistance based heating or electrode based heating. And foundries in Japan and in other parts in Norway have shown that they use some of the electric ladles. In US in 1980s and 90s, there were larger number of a larger number of customers using electric ladle, but now there are only a handful of foundries that are using electric. Most of them are using natural gas because of the cost and other reasons. So let's take a few minutes to understand what are the current methods and um, why and what are some of the challenges in the current methods. The current method is using natural gas or liquid petroleum gas or oxy-fuel, and as I told you, uh, the combustion gas, 80% of the heat generated from the combustion process escapes out through the lid and goes to the atmosphere. And many times there is no heat recovery process that can reuse the heat that is wasted to the atmosphere. This is a big loss of energy, and it's a very wasteful form of energy. The heating is many times an open loop process. What do I mean by that is the temperature is not controlled with the sensor or a controller. So the natural gas heating is continuously occurring from the time the ladle starts to heat until it is ready for it to go and grab the molten metal. So until that time, from pour to pour, they call it a pour to pour, it is going to be heated. Even if the temperature has come to the set temperature, it is continuously going to be heated because it is an open loop process. 80% of the heat escapes to the atmosphere, and because of the open lid, there are possibilities for oxide or oxygen-based residues or slags that is being generated on the surface of the molten metal. And the last but not the least is worker condition. Because of the smoke, if you can imagine in a foundry, it's a clean room. You are seeing black smoke coming out of this uh, combustion gas. It's very noisy, it's loud, and it's so much heat is generated around the ladle heating preheating area. So it gives a poor work environment to the workers. So here is a quick example of a very small foundry using natural gas for preheating their ladle. So on the left image, you are seeing the back side of the heater where the natural gas pipeline is coming to a burner, and once the burner starts the fire, in the right hand side picture, top picture, you will see a small hole, and there is a black uh, smog around that hole, and that's where the natural gas burner starts the flame, and you can see the ladle being inverted, so the natural gas goes directly to the bottom of the ladle, and then the combustion gases escape through a escape channel, and it goes directly to the top of the roof and let go of the facility to the atmosphere. So most of the heat just goes away as wasted heat to the atmosphere. So why it is not a best way to preheat a ladle? Why natural gas or other fossil fuel based method is not a good way to preheat ladle? There are some drawbacks. I can uh, go through that in a minute here. First and foremost, it has a low thermal efficiency. In a bigger ladle, it can go up to 15% efficient, but in smaller ladles, only 5% their thermal efficiency is. I'm not speaking about the burner efficiency, but the efficiency of heat transfer to the ladle. The reason is 80% or more of the heat just hits the ladle and escapes out to the atmosphere. So it does not give enough chance for the refractory material to absorb the heat. And because of this, it causes undesirable high temperature near the workplace. So when all of the natural gas ladle preheating station operates, operates, it's very hard to go near it because the temperatures is very high around that area. And one of the primary reason for preheating is to eliminate moisture content. But if you look at some of the combustion gases that come out of burning natural gas, methane and ethane are two major components in natural gas. And if you look at the equation of the chemical reaction, the outcome of the combustion is carbon dioxide and water plus energy. Energy is the heat energy, that is the exothermic reaction, which is goes to the ladle. But one of the byproduct is water, and this is trying to put moisture in where you are trying to remove moisture out of the ladle. So it's one of the reasons, a big drawback. poor air quality, and also sometimes it leads to poor product quality because of the contamination that may occur because of the combustion gases when molten metal is in contact with the oxide of the inner wall. And whenever there is natural gas, there is a high risk of explosion that the plant manager should be aware of. So these are some of the challenges in natural gas ladle preheating. Let's turn the table and see how electric ladle preheating works. There are different types of electric ladle preheaters. In US, in 1980s and 90s, we used electric resistance based preheating, and there are electrodes based electric ladles, and we are also trying infrared and induction based ladle preheating as some new design elements. And the reason why the electric ladle was even considered in the past, in 1973 there was a projected shortage of natural gas, and hence the interest began to develop use of electricity. But if we look at the current state of natural gas, there's a lot of natural gas available in US, and so the interest is not that high, and that's the reason why we have only few foundries that still use it. And when we talk to those foundries, they still say that the electric ladle operate better and have better operating characteristics, and they reduce cost. But traditionally it has been natural gas heating, so the industry still has a lot of time to come to that point of utilizing the electric ladles. So here I show how does electric resistance ladle works. In electric resistance preheater, the heat transfer is done through radiation and not by conduction. So whenever there is a heat transfer through radiation, the equation or the law that comes into play is the Stefan Boltzmann law. And I have on the right corner top, you can see the law. And one of the interesting or important characteristic is the temperature is raised to the power of 4. So any small increment in temperature to the resistor element can give a big difference, big output to heat the ladle, and that's why it is very efficient. And in practice, we can go only so high in temperature in the resistance element themselves, so that it won't burn or melt. The maximum temperature is about 2000 degrees for metallic element and 3000 degrees for graphite based resistive element. And you can see there is a controller and a transformer that can adjust the flow of current to heat the resistor heating element. And because of this control, we can raise it high or low to increase the heat or reduce the heat and have a controlled closed loop environment. So EPRI has done research in 1988 working with some of the major foundries in US, and they were trying to evaluate the natural gas and the electric version of the preheater, of the ladles. And what they found is very interesting. They were measuring temperature in a ladle or a ladle at various points. So TC stands for thermocouple. They kept thermocouple in different locations, from upper sidewall, lower sidewall, bottom, and well block. So they kept in different locations, and in one method they use natural gas, and in second method they use electric, as you can see in the right top corner picture. And over a period of time, this is a very early rudimentary stage of electric heating. They were able to see the electric resistance heating was very comparable in terms, in fact sometimes better than the natural gas. and they were able to come to the same temperature band within a time frame of 6 hours. And this is just to show that temperatures could be reached um, of the same temperatures that the natural gas could reach were able to be obtained by the electric ladles also. There was a misconception at that time that the electric elements cannot uh, heat the ladles to the same temperature as natural gas. So this helped to justify that electric ladles indeed could reach that temperature. And uh, for some of the molten metal temperature, you can see down, like for example, carbon steel, it's about 3000 degree Fahrenheit. So that's the ladle should be around 2500 to 3000 degrees so as to reduce the heat loss to the ladle. So they were able to reach that kind of temperatures with electric technologies at that time. And so uh, the important discovery from that is that the gas-fired preheaters, to reach the same temperature, they were using 35 million BTUs, while equivalent of a 10.5 kilowatt hours, while the electric preheaters used only 3000 kilowatt hours, so nearly a reduction of 70% energy. And if you increase the energy a little bit more, you could reach the temperature even in a shorter period of time. So there is a big difference in the amount of energy used to reach same temperature, same outcome of the ladle. So this all proved that electric ladles work, and a closed loop control is possible, and energy could be lowered with electric ladle method, electric preheating. And this is an example. I provided the link below where a foundry in Japan was using electrode-based preheating. And there are some distinct advantages of this ladle. First thing to note is that um, the lid of the ladle could be completely closed, while in natural gas the lid has to be open. It cannot touch uh, the lip of the ladle because the combustion gases need some place to escape. Because there is no combustion here, the lip can be completely sealed with the cover, and the heat could be only contained within the ladle. And and in some cases, nitrogen or other inert gases could be sent through the uh, through the cover, so that there is no oxygen inside the ladle to prevent it from any oxidation or any slag. So some of the benefits of this is energy savings, higher effective heat transfer, and improvement in working conditions. Because we contain the heat within the ladle, the outside environment is not as hot as natural gas. And more heat is transferred to the ladle than natural gas combustion, and less oxide residues or slag formation because we are using inert gas to remove oxygen out of the ladle. So these are some of the benefits that the industry has seen. Uh, there are there could be other benefits as well. Um, the next maybe couple of minutes, let's look at the worker safety and indoor air quality, which is a big deal to the facility. If if worker safety is not taken care, then the production and the productivity of the facility will suffer dramatically. So let's take a look at some of the health and safety concerns. If you look at the foundry, as I told before, it is not a clean room. It has dust, it has smoke, it has noise, heat, and it's not an ideal condition to work for. Um, there is also an added risk of explosion. And in US, there is an organization called OSHA, which is Occupational Safety and Health Administration. And this considers some of the indoor contaminants, lists some of the indoor air contaminants. And the top few of the contaminants are carbon dioxide, carbon monoxide, nitrogen oxides. Commonly, we call it NOx, NOx, or even SOx, SOx. The nitrogen oxides are formed during the combustion process from gas furnaces. And as we saw before, one of the byproduct of the natural gas combustion is carbon dioxide. And that is a lot of carbon dioxide and particulate matters that come out of that smoke when during the natural gas preheating. So that all these reasons lead to some of the health concerns for workers. Some of the hazards of workers working in this kind of environment is poor indoor air quality, and this may lead to headaches or fatigue or trouble concentrating on their work, a lot of irritation, eyes, nose, throats, cough, affecting the lungs, asthma, and in some cases even cancer after prolonged exposure to harmful air pollutants. And as a matter of fact, I was there at this one Foundry customer, and then it's we spent only a day or two, but when I came back, I can still have my clothes and everything was still smelling like the Foundry. So it's a long-lasting effect of the smoke and everything, the particulate matters surrounding that place near the ladles and the furnaces. The ladle preheating adds to that particulate matter. So in essence, the electric ladle preheater improves the worker environment. Um, we know that the environment is not very desirable in foundries, so any reduction in air pollution or noise is helpful to the worker environment, and electric ladles does that, and they do not produce on-site emissions, so that helps in reducing the air pollution, significantly reduces the risk of explosion, and the heat is contained within the ladle, so surrounding environment is not heated. So these are some of the benefits that we can pass on to the workers so they can have better improved working conditions. So as a last segment, I would like to cover some of laboratory testing of some new designs of electric technologies. We were able to gather an example of a ladle used in this small foundry, and you can see it in the top right corner how the ladle looks like. It is one of the design that is called a teapot spout ladle. So it has a spout at the bottom from which the molten metal comes through the spout and pours through that lip. So we, in order to evaluate design of two different methods, one using infrared heating and second using inline resistor heater, which is 30 kilowatt capacity. We use this as an example. We placed different thermocouples. Uh, we placed several thermocouples on this ladle. Two of them are on the inner surface, one inside the refractory material and one inside the spout. So the actual picture showing how we placed it. On the left top corner, we had a T construction, a T-type construction where the infrared element was hanging inside, and we covered the lip with an insulating blanket, so the heat could be contained within the ladle. And this is a small 2 kilowatt element, and just wanted to keep you aware that this is just an experiment that we are doing. You can increase the size of the infrared, the capacity of the infrared element to add more heat to the um, to the ladle. And in the second case, what you are seeing is an inline resistive heater. Uh, it is there is a small blower pump that pushes the air through the inline heater, and at the end we have a insulating board which closes the lip of the ladle, and the heat is forced into the ladle and escapes through the lid. So this is similar to the hair dryer that we use. It has a blower motor and a resistive element, and air that is coming out of that through that dryer is hot. So it's same principle. So we had some interesting results looking at um, the uh, we had two test results, one on the infrared heater and one for the inline resistance heater. And you can see that in this case, the top line TC1 reached up to 330 degrees Fahrenheit. Um, and at that point, the customer originally mentioned that they were they were heating a metal that has a lower temperature. So they said if the ladle is more than 250 degree Fahrenheit, that should be fine. So we were trying to reach more than 250 degree Fahrenheit at this time, but later found they wanted it to be more than 700 degrees. So in this case, we were able to bring it up to 330 degrees within just 1 hour time frame. But you can see that the spout was still around 100 degrees. It did not heat up because there is no airflow. That is because there is no airflow that is happening inside the ladle. So the spout, which is outside of the ladle, did not get heated up. So we need to send hot air or blow some air to get the spout heated. So that's one of the reason why you'll see it as 104 degrees. So this is a good learning experience for us to understand how the heat transfer mechanism operates for different technologies. The wall temperature of the ladle was, we were able to raise it to 265 degrees Fahrenheit within an hour. Um, Similarly, we did it for inline heaters, but the inline heater, since it was 30 kilowatt, we were able to raise it to a higher temperature to 445 degrees to the 445 degrees around the mid region, and then 388 in the bottom, and the spout was 353 degrees. The reason the spout is at higher temperature than the infrared is because this is a hot air blower. So as the hot air escapes through the spout also got hot. So that's one of the reason why the spout was able to go higher than the previous case. And we are able to reach 320 degrees plus wall temperature within a short 45-minute heat up time. So the reason why the temperature, there's a difference in the wall temperature versus the inner temperature is that it all depends on the inner lining. So here is an example how the inner lining affects the outer shell temperature. If uh, so, in the second in the mid-level section, what you see is a grayed out cell. It's the insulation refractory, and the dark gray is the hot phase refractory. Hot phase refractory is the one that gets in touch with the molten metal, and if there is no insulation, like in the first case, there is no insulation refractory, most of the heat is passed on to the shell. So the shell temperature, the outside shell temperature is at a very high temperature, 280 degrees. But if you have insulation refractory, then it prevents that the heat going to the shell. And if you do not have the insulation, what happens is you need more heat to put in, because most of the heat is coming going to the shell and escaping to the atmosphere. So you want to have a balance of the insulation and hot phase refractory to maintain the shell temperature as close to an ambient temperature as possible. So here is an example of the thermal images that we took of a natural gas preheater in operation. So we are seeing the shell temperature of 720 degrees Fahrenheit. The inner temperature is about 1200 degrees Fahrenheit, and so a lot of heat is transferred to the shell, means that it has a lower insulation refractory. So we did some very high level energy comparison using electric and natural gas. This is just not to be treated as the final, but just a comparison to see what kind of savings that we can see in terms of at least the ratio in terms of electric versus natural gas. With the natural gas, with the electric, 10 kilowatt heater plus 1/20th horsepower blower, we are able to use 36, nearly 37,000 BTU to reach the temperature, while for natural gas it required 225,000 BTU to reach the same temperature. So that means at least six times better than better energy reduction than natural gas. So this is just an example once again to show that the electric technology could operationally operation wise can draw less energy to reach the same outcome. So finally, the advantages that I already mentioned, but some of the other advantages of electric ladle preheaters are improved safety, less heating of workspace, no exhaust emissions, improved working conditions. Um, the operation cost is less, and they will produce a thorough dry lining and will not introduce water vapor in the process, which is there is no byproduct, or there is no water vapor during the process of heating, and they could have a higher energy efficiency of 80% or higher. Um, there are other approaches also. For example, Inductotherm is a company that uses a process called automatic pouring systems. So where the molten metal is directly from the melting furnace directly go into a pouring line, and it is casted into parts. And in this method, they can avoid ladle. Uh, well, they can remove or eliminate the use of ladles. But once again, this requires the foundry to be reorganized and restructured to have this kind of operation. But this is another example how we could increase the efficiency. In summary, we can reach more than 400 degrees through different methods, and we are still in the process of identifying some solution by working with some of the vendors in US to come across a neat solution, a turnkey solution that could benefit the um, foundry industry. And we are working with a couple of partners, both from the makers of the ladles and the makers of the heating, and trying to come to a collaborative effort to find a common solution that could help this industry. And these are some of the other sources that you could go and take a look at some of the previous works that has been done. In fact, American Foundry Society has some very good journal articles. In fact, I have listed some of them here, which shows the actual working of the electric ladle in various foundries. So these are some of the examples that you could go back for a resource. So with that, I think I've covered my topics, and would like to